Welcome to today's Explainer. Today, we're unlocking a hidden world. It's a world of invisible forces, frantic, microscopic movement, and yeah, sudden, shocking energy. We are literally surrounded by millions of tiny, unseen particles that are constantly engaged in this highly energetic dance. They dictate exactly how the physical world reacts around us, and sometimes, well, they use us as their literal dance floor. Okay, let's dive into this. Have you ever gotten a sudden, sharp zap when you just reach for a metal doorknob? Or, stood in front of a mirror battling wildly frizzy, floating hair on a really cold, dry winter day? These are super relatable experiences, right? But they're actually your direct, undeniable encounters with the abstract physics of static electricity. It's basically the universe reminding you that invisible, dynamic things are happening right beneath your fingertips. So, what exactly is it? Static electricity is simply the buildup of electric charge, either positive or negative, in one specific location. Scientists actually call it electricity at rest, but don't let that serene little phrase fool you. To create this so-called rest, an absolutely staggering amount of hyperactive invisible motion has to happen first. Section 1. The invisible dance of electrons, uncovering the root of the charge. You see, electrical charge is a fundamental property of matter, and it operates on some very strict kinetic rules. When you have two charges of the exact same kind, like say two positives or two negatives, watch them violently snap apart. They repel each other with this sudden, invisible force. But if you place two different charges near one another, one positive, one negative, they smoothly, magnetically glide together until they connect. Snap apart, pull together. That push and pull is the engine driving this entire phenomenon. Now, most of the time, the world around us is beautifully balanced in a neutral norm. Objects typically experience an overall charge of 0. They have perfectly matched numbers of positive and negative charges, and they're completely content just sitting there. So, for an object to suddenly get a charge, that perfect balance has to be disrupted. Something physical literally must be moved, bumped, or forced entirely out of place. So the crucial point is that static electricity is entirely a game of moving microscopic pieces, specifically electrons, from one place to another. Accumulating a charge absolutely requires the active transfer of electrons. If you pull negatively charged electrons away from a surface, well, that surface is left with a positive charge. If you force extra electrons onto a surface, it becomes negatively charged. Picture electrons jumping dynamically from object A to object B. Object A loses them and becomes positive, while object B traps them and becomes negative. Section 2. The friction factor, the triboelectric effect in motion. But how do we actually force these electrons to jump ship in our everyday lives? Usually, it's through friction, formerly known as the triboelectric effect. This is simply the transfer of charge from one object to another when they're rubbed together. Now, this effect heavily relies on objects being electrically insulating. That just means electrons cannot freely flow or escape. So, when two insulating materials are rubbed together, the friction literally rips electrons off one surface and traps them right on the other. Let's watch this sequence unfold. Step 1, you shuffle your fuzzy socks rapidly across a dry winter carpet. That's your friction. Step 2, those invisible electrons are torn away, transferring and building up on your body with absolutely nowhere to go. Step 3, you reach out and touch a highly conducting metal doorknob. Step 4, those trapped electrons suddenly have a superhighway. The charge violently rushes out and, zap, the tension breaks. And this brilliantly illustrates that this whole process isn't just random. Scientists have actually mapped this out in what's called the triboelectric series. It's literally a predictive list showing exactly which materials will become positive and which will become negative after separation. We can mathematically predict the outcome of this invisible, energetic dance. So yeah, science knows exactly why aggressively rubbing a balloon on your head makes your hair stand straight up. Section 3. Conduction versus induction. Other ways electrons make their move. Let's contrast conduction and induction. Conduction is all about hard physical bumping. It involves the direct transfer of electrons when objects physically touch each other. A charged object taps a neutral one, and the electrons just spill right over. But induction? Induction is far more fascinating. It involves zero transfer of electrons and absolutely no direct physical contact. Instead, it relies entirely on that invisible, eerie push and pull. That spooky action at a distance of electrical repulsion and attraction. Let's move to and see how this builds in a real induction scenario. First, imagine two conducting metal objects, A and B, physically touching each other. Next, We bring a highly negatively charged object close to object A, but we don't touch it, because like charges repel, the negative electrons inside object A panic. They slide away, migrating right over into object B. Finally, while that invading object is still hovering nearby, we physically separate A and B. The result? Object A has been drained and is positive, while object B has trapped the electrons and is entirely negative. A complete transfer without a single drop of direct contact. It's almost like a magic trick.
Section 4. Taming the static, grounding the invisible dance.
So remember this rule. Because electrons cannot freely move on insulating materials, those surfaces remain charged for a very long time. That trapped energy is the root of the classic static annoyance. Your socks sticking to your towels in the laundry, or your favorite sweater clinging to you. It's all just trapped energy, desperately waiting for a conductive escape route. Now, what's really interesting about this is how beautifully simple the solution actually is. The source material points out that adding water to frizzy hair removes the static. But why? Well, because everyday tap water or rainwater contains dissolved ions, which makes it electrically conducting. By simply running a wet hand over your wild hair, you provide a conductive pathway. You are instantly neutralizing that chaotic electron buildup, finally giving that electricity at rest a place to go. It really changes how you look at a simple carpet or a doorknob, doesn't it? Knowing that every shuffle of your feet, every sweater you pull over your head, and every touch of a metal surface involves the rapid kinetic transfer of billions of tiny particles. What invisible electric dances are happening around you right now? Next time you get a shock, remember, that's not just a zap. That is the grand finale of a microscopic high-speed electron transfer. Keep looking closely at the active world around you, and thanks for exploring this explainer with me.